This is section 1.1, a preview of calculus. So what we need to talk about is what is calculus. So we split calculus up into two different categories. The first category that we'll be dealing more with this year is differential calculus. And with differential calculus, we study rates of change, slopes, and we break functions down into small pieces and look at those small pieces. Integral calculus, which we will address toward the end of the year, helps us find areas and volumes, and it's where we put pieces of a function together and look at that little bit bigger picture. So we want to talk about what we could do without calculus and then what we're going to be able to do with calculus. So the first thing is slopes. Back in Algebra 1, if we were given a line, we were able to find the slope of that line using rise over run. With calculus this year, we're going to be able to look now at a curve and say, okay, what is the slope of that curve at this point? That also allows us to figure out rates of change. So remember, slope is another word for rate of change. So when we talked about rates of change in Algebra 1, we talked about how if I run a mile in 8 minutes, we can talk about my average speed. Well, usually, especially for me, when I'm running a mile, I don't run the same speed throughout that entire 8 minutes. I'm usually faster and slower, maybe even walking, whatever. So calculus is going to allow us to find instantaneous rates of change. So what was my speed at a particular moment? The next thing, when we talk about without calculus, if we are looking at a curve, we would mostly use secant lines. So remember, when we were calculating slope, you need 2 points, so we would use a secant line. Remember, a secant line goes through the curve at 2 different points. Now with calculus, we're going to take that and we're now going to look at tangent lines. So review, tangent is where it crosses at 1 point. Okay, so what is that slope of that line that hits that curve at 1 point? Next thing is area. So without calculus, we were able to find areas of normal shapes, okay? So remember, we talked about a rectangle. Remember, base times height, a triangle, base times height divided by 2. Now with calculus, we're going to look at shapes that aren't so nice. So maybe something that looks like that, okay? Something that doesn't have a direct formula. The same thing works for volumes. Without calculus, we talked about volume and surface area of a normal solid. So maybe a prism or a pyramid or a cylinder. We have formulas to find volume or surface area of those. Now, with calculus, we're going to be able to do that if it's not quite so nice and it doesn't have a strict formula. So let's talk about differential calculus. With differential calculus, we're going to look at the tangent line problem. So if I have let's say I have a function that looks like this, and I specifically want to look at this point. Normally, to find that slope, we would have to estimate by drawing a lot of smaller tangent lines, okay? So we would say, all right, maybe this line is a good estimate. Well, what we really want is we want that slope of that tangent line. That gives us the actual slope at that point. So what calculus does in differential calculus, we take that secant line and we keep drawing it until those points, the 2 points that we use, are so close together that we get to that actual tangent line. And that's how we're going to find slopes of curves. So what we want is we want 2 points that are closer together. So on this first one, we had 2 points that are pretty far away. well, this one looks a little bit more accurate, and this one looks more accurate still until we get to a tangent. With integral calculus, instead of slopes, let's talk about area. So I'm going to draw this nice curve here. So just how with slope, okay, we know how to find the slope of a line. We want to find that area underneath this curve here. What integral calculus does is basically taking, let's take a shape that we know, like a rectangle, and let's try to estimate by drawing a bunch of little rectangles. Okay, and that gives us an estimate. And just like how with differential calculus, we kept going until we were so close together that it was essentially a tangent line. What we're going to do is we're going to make these rectangles smaller and smaller and smaller until we're so close that we're accurate. And that's how we're going to find areas using integral calculus. So that's my introduction.